Hello. Yes, so recording has started. Let's start. So my name is Annika Neidhardt, and I have had the pleasure to be invited to this webinar. I'm a senior research fellow at the University of Surrey at the moment at the Institute of Sound Recording. And my main research topic is audio for augmented and extended reality. And today I will talk about audio for extended reality. How can we create auditory illusions in the natural environment? So first, I would like to maybe distinguish the different types. So I mean, virtual reality is usually virtual reality is what I would call it, or the terms are used in different ways. And virtual acoustics or virtual reality is when we create a whole virtual environment around the user. But in augmented reality, I use the term in a way that we add virtual content to the real environment. And with extended reality, what I will be today is the case where we modify the appearance of the natural environment in addition to just adding virtual contents. So it will be a whole mix of virtual content that we add, but also modified appearance of the real environment. Yes, but let's start maybe with augmented reality or extended reality and why it matters. So on the one hand, there have been interesting studies, or there are more and more studies that explore these technologies for healthcare, for example. So we think of creating convincing illusions in the real environment. We could use that for treating phobia or depression or ADHD, for example. We could create specific environments or environmental cues, or also social situations, for example, to treat social anxiety. That would be one interesting field of application, maybe, and education. And when we can create virtual contents in the real environment, then it can also be very useful to make things more accessible in the field of learning. So it would help or make it easier to explain complex concepts and kind of make it more clear to the students or the ones to learn something. And of course, it can also help to reduce loneliness, to create more social exchange also over long distances without having to travel. And another field is, of course, the field of art. So when we create or when we can mix virtual contents with the real environment and maybe even modify the appearance of the real environment, then that is a very promising platform for creating very new types of art and develop very new concepts. So that are just a few example applications, but there are many more. For example, also virtual prototyping, of course. And yes, so augmented reality, extended reality can make the lives of people better, of several people. So I think it's interesting to explore this technology, but it's of course only interesting if it works. So that is still a bit of a challenge, but let's look into that. So how can we create auditory illusions in the real environment? The best case is when we measure the room impulse responses or the binaural room impulse responses for a specific listening position in the room and a specific source position in the room for the virtual sound source where we want it to be. And the best case is if we measure it with our own ears. So some colleagues from the university have conducted a very interesting study where they put a lot of effort into being very accurate with their measurements. That was Brinkmann et al. 2017, and they put a lot of effort into measuring with in-ear microphones for the different participants. So they had individual recordings of the binaural room path responses, and they had related cues. And they used those measured binaural room path responses to convert it with some dry signals. And with this setup, they were able to achieve what we call authenticity. So perceptually indistinguishable auditory illusions that sound just as the real version of this same scenario. And that has been a very historic moment in binaural audio because, for example, in the visual field, we are still not able to create visual illusions that are completely indistinguishable from the real versions. So that's interesting, and we can do that already in the audio field. But to be fair, it was only achieved for speech. And the same experiment was conducted with white noise bursts, and there the participants could still distinguish virtual from real. Yes, but it was a very critical test scenario. So with ABX, that's a very critical test paradigm. And what we actually want, or what would maybe be enough for what we want to achieve, is that we accept the virtual contents as real. So that's already a pretty high goal. That's maybe rather called plausibility, or let's look into that construct a bit more. So plausibility is used when or describes the degree of alignment with the user expectations. So very good plausibility is achieved when the expectations of the listeners are met very well. So one very high goal would be that the user accepts the virtual contents as real. So it might still sound slightly different, but if we don't have a direct comparison, for example, then we would not notice that it's virtual. And that's of course still a very convincing illusion. But another also interesting degree of plausibility is when we know that it's virtual, but it still makes sense in the given scenario. And it still meets the user expectations. And one interesting example maybe is that if we are in the Harry Potter world, and somebody gives us the context that we are in the Harry Potter world, but we just see the same scenario, we just hear the same things, but suddenly somebody would fly on a broom, then we wouldn't be surprised anymore. It would be plausible because now we know, okay, that's the Harry Potter world, and there people fly around with brooms. So that's one example of plausibility. And when we think of plausibility and user expectation, we might have to distinguish different levels of detail that we want to achieve. So I spoke about this acceptance as real with the first, like here we have a visual representation, and with the first picture we would have like the acceptance as real because that looks very convincing, very realistic. But then we have still different levels of details or levels of extraction, or degrees of abstraction maybe, where in the second picture we still have the shape and the texture and the color. In the third picture we still have the shape and the texture, and in the last one we just have the shape. But for all of these we can still see that it's a can, it's a convincing representation of a can. And of course we can see that it's not real, but it's still plausible, right? So that is something we can also transfer to the different degrees of plausibility in the audio field. So we might have a very realistic representation, or some abstraction where we notice that it's not real, but it still makes sense and it might do the job. That's interesting for earcones, for example, that could be used for navigation in the real world. And then you just need a certain abstract sound, for example, that gives a certain direction, and that could be interesting content from that. When we think about plausibility, I also want to refer to one study that looks at that in a slightly different way. They don't really create spatial auditory illusions, maybe, but they have this box, this Schrödinger's box, where you cannot tell what material it is made of. You can take this small hammer and knock on it, and then hear how it sounds and find out how, yeah, maybe find out by listening to the sound which material it is made of. But the funny thing is that every time it does a different sound, and you have to find out which one might be the real one. So sometimes there's a metal sound or a wooden sound, and some of them sound very convincing, so it could be the real material. So that's also an interesting example where plausibility matters, or where we can, look at that. But when we go back to augmented and extended reality, the user expectation will be formed based on several experiences that we've made in our previous life, and also by the environment that we are in. So we have, on the one hand, the external reference, and on the other hand, the internal reference. So the internal reference is what we've learned over the years, how things sound. And the external reference is the environment where we are in that specific moment. And between the two, there's also a certain exchange. So certain aspects of the real environment at the moment will influence the internal reference, and the other way around. But all this together forms the listener expectation. So when we want to create virtual contents and or virtual elements that we want to add to this environment, it needs to be matched perfectly or like perceptually well enough to blend with the real environment. And there are certain requirements, perceptual requirements that need to be met, but they are not fully understood yet. So we've learned some things about that already, and I can share some more information on that throughout this presentation. But we still need to learn more. We still need to study it in more depth to understand that in more depth. Okay. So, and another interesting scenario when we think about plausibility is the social interaction. For example, when we use social virtual reality or social mixed or extended reality, then usually the user engages in some social interaction or some communication, and is often pretty busy with that, like cognitively. And we don't have this typical listening scenario anymore that we usually have had in listening experiments. And the question is how that influences how we perceive the acoustics. Do we pay attention to that? So how accurately does it need to be? How can we evaluate that during this interaction? These are questions that have not been solved. There are some early studies that look into that and try some different approaches. But so far, I don't have the impression that the test methods are really suitable. I think that there we need to explore more indirect measures or behavioral measures, maybe, that we can measure during the interaction of the users. But that's a different topic. So now we know what we want to achieve, plausibility. Let's go to the questions how we can get there. What are the technical approaches? So we talked about that measuring a binary room pulse response in the specific position and orientation in the room, exactly where the listener will be placed later, will be a very promising approach. I have here one picture of a setup that I used. I placed the dummy head in certain future listening positions, and that usually works pretty well because the auditory sense aligns very well with the other senses, and that usually creates a very convincing auditory and multimodal illusion. So, of course, when we want to have a whole when we want to create a whole listening area, we would have to measure it again for each change of the position of the listener, and also for each change of the position of the sound source. So every time the listener changes, or the listener moves, or the source moves, we need to adjust the binary room path response. And to create a whole listening area, we would have to conduct lots of measurements. And for that, some helpers have been developed in several different labs, for example, in Aalto, the university in Finland, or in Ilmenau in Germany, or in Illinois in the US, or also in Lucerne in Switzerland. But that's just a very small selection of robots, measurement robots, that have been developed for these kind of purposes. With those, we can cover a certain grid in a room. Here is just a very small example of a grid that I have measured. I placed the dummy heads in 25 centimeter steps along a 2 meter line for 2 different sound sources. And with such a setup, when we want to be in line with the spatial sampling criterion, we have to measure every 4 centimeters for 4 kilohertz, upper frequency limits, and in a 2 centimeter grid for 8 kilohertz upper limit of the spatially correct sound field. But that's, of course, a lot of efforts to measure that in this detail. So that's not what we want to do. But how many measurements we really need depends on how we recreate or create the binary room and path responses for the whole listening area. So we don't have to measure them all, but if we measure at certain selected positions, then we can use interpolation or extrapolation and create all the other binary room and path responses for the whole listening area. And over the past years, past five years, so many different approaches have been proposed for that. For example, by Garcia Gomez, based on dynamic time warping, or the shaping of the initial time delay gap, based on different deep learning approaches, or also the extrapolation from spherical microphone array data. So these are just a few examples of approaches that have been proposed. And it is also possible to, when we have certain sparse or selected positions that have been measured, from this data we can also reconstruct the sound fields to a certain extent. And there again, some interesting works have been proposed. There's a study where we have done that ourselves. We used 24 positions of binary room and path response measurements just in one direction. So not for the whole round, because that's also quite time consuming, but just all in one direction, all dummy head positions rotated in one direction. And then with that, we could recreate the whole, or reconstruct the sound field over a whole listening area, and use inverse optimization to describe the sound fields as a superposition of equivalent sources that reproduce sound. And with this description, we can then generate the binary room and path list over the whole area and don't have to measure all the different positions. And another interesting approach that has been proposed already a while ago is just based on a single mono room and path response that was measured in a room. And from that, a kind of upmixing approach was used to create binary room and path responses for a whole listening area. But that will not be physically accurate anymore, but it's a perceptually motivated approach. And with those, we can save a lot of measurements and we can create very efficient rendering. But these are all the approaches that we can use based on measurements. And And we need, of course, a good understanding of perception to optimize that, how much we can simplify that. But another approach is just to use acoustic modeling or a simulation of the sound field instead of measuring it. But it still needs to be perceptually matched to the acoustics of the real room. And here I've borrowed a nice overview graphic that shows the very different methods that are available, or well, still a selection, but a nice overview of physically based acoustic simulation approaches or delay network approaches that have a certain connection, of course, to the actual physics, but are still already pretty simplified, but on the other hand, very efficient in how much effort they need for the calculation or how much computation power they need. And again, the connection to the measured room impulse responses, because they can be convolved then with the tri-signal. So that's an overview. We can use all the different methods, but next picture. It's also good to keep in mind that certain methods are like more useful in the specific frequency ranges or for specific time ranges. So, for example, for the early part of the room impulse response, we already know that humans are more sensitive to the details of the acoustics. So it makes sense to be more precise there in the simulation. And for the later sound fields in the room, we know that humans are pretty insensitive to most of the details, so we can have a very simplified representation of that. And we know that for the lower frequencies, wave-based methods or finite time domain methods are good approaches to model that in more accuracy. So at this year's DAFIX conference that was here in Surrey, we had a very nice tutorial by Ochi-sama Das, who also provided some nice toolbox on GitHub. So I wanted to share that with you. But when we model room acoustics in general for augmented reality or extended reality, the question always remains, how accurate does it need to be? How close do we have to get to the real physics of the room? How close do we have to get to the sound fields that would be created if the sound source was really in this room? And what are the user expectations? What can we simplify to still meet the user expectations? So that's important to keep in mind. And then we have another technical constraint when we want to create these auditory illusions. We need to take into account that we use headphones or hearables, and there are two different approaches to achieve transparency. So we don't want that these headphones or hearables are too influence too much how we perceive the real environment, the real acoustic environment. And there's one approach, is the acoustic transparency. So the headphones or hearables could be designed in a way that there's still enough space. So for example, we could have extraoral headphones which are far away from the ears or from the ear entrance, so that still the acoustics of the real sound field can kind of get through. Or we can have electroacoustic transparency, where we kind of close the ears, but we have some microphones outside, and then we can let the sound field pass electroacoustically. So these are two different approaches that can be used. We conducted a study where we just used a selection of typical headphones, extraoral headphones, and also some open headphones. And what we could find out there in a listening experiment in the comparison to a measurement without headphones is that for some of the headphones, it was really just a minimal influence of their presence. For example, the BK211, which is a prototype for research, and it's the one in the first picture. But it's pretty big and heavy, and it's not super practical for 6 degrees of freedom experiments where people can walk around, because then they are very careful in moving around. Another typical headphone that we can use is the AKG K1000. That has been included in this study as well in 2 different configurations. One is where we used it in a 0-degree angle, and one is where we used it in a 45-degree opening angle. But here we can also see that the influence is just rather small compared to many other headphones. For the strong influences, the participants said that on the one hand, coloration was affected. On the other hand, also the localization was affected. And even externalization was affected in some cases, and the localization only happened in the head. So there have been interesting new works that model these different influences so that we can predict the transparency of certain headphone devices or head-worn devices. So coloration, localization, and externalization are typical things that are influenced by headphones or hearables that are not, that if we don't compensate for this influence. Okay, so perceptual requirements, how accurate does it have to be? So when we walk into a room and we see this room, and one question is, what do we expect from this room? How does it sound? So on the one hand, we have the visual impression of the sound source, and on the other hand, we have the visual impression of the room and of the sound source. When we don't get the room acoustics right, it can influence the apparent source of what we hear, of the sound source, the apparent source. It can influence the direction or the localization and distance. It can also influence certain coloration effects. So we, from our everyday lives, we have a certain expectation, for example, how a loudspeaker would sound if we play some music with it, or reproduce some music with it, we have certain expectations to, if we see a sound source, how it sounds, if that sound source emits sound. And on the other hand, we have certain expectations towards the room, but we don't have a good understanding of that yet. So, I mean, in terms of research, we still have an only very rough idea of what listeners expect when they see a room. So that's still a subject to research. And to investigate that in more depth, we can use a virtual environment, because there we can create sounds or room environments or acoustic environments that are not known to the user, and so we can find out what just the visual impression, what kind of expectations they cause. So we have had this kind of office space, and we have had this picture or this spatial visual representation of a server room, and we created different sizes of those 2 rooms, and we could find out how the visual size influences the expectation towards the reverberation time and the acoustic room size. So if we want to find out how what listeners expect with regards to the early reflection pattern in a room, for example, that is something we tested with this scattering delay network. And we had a room model which was adjusted in size by the participants, and that changed, on the one hand, the acoustic size of the model, and then there was a second slider that changed the absorption coefficient, so that overall the reverberation time was adjusted, and the listeners didn't know what they were adjusting. They could only hear what they were adjusting, and it was interesting to find out they expected. So for the effect on the visual size, or the effect of the visual size on the expected reverberation time, we could on the one hand show that with increasing size, also an increase in reverberation time is expected, but this connection is not linear, but linear. And we modeled that with a with Stephen's power law. That seemed like a good approximation, but of course it's a very small data set because we only used 2 different rooms and 3 different sizes, which is not really representative for other rooms out there. So this needs to be studied in more depth. And we look at the expected acoustic size, the size of the acoustic room model. Then we can also see that with the increase of the visual size of the room, the expected size of the acoustic room was growing or increasing, but not as strong as we would have expected. So we see that the visual size was increased up to over 600 cubic meters, but the visual expectation, acoustic expectation, did not rise to the same level. So again, we have just a nonlinear connection between the two, and this is what we want here. But this needs more investigation with larger data sets to get a clearer picture of that. So, and that was about the reverberation time, but what about the early reflections? So again, we see a real room and we see a loudspeaker in there, for example. I conducted measurements with a dummy head where the loudspeakers were flipped, so they were turned away from the listening positions, and the listener could only see basically the back of the loudspeaker, and the loudspeaker was playing away from them. So the direct sound that arrived at the listening position was pretty low in energy. In that case, the listeners are usually much more sensitive to the details of the early reflections. And what I studied here was, or what I tried here is, I used the binaural room impulse responses that I measured along the line, and I used the early and the left and the right channel, and swapped them directly after the direct sound and 50 milliseconds after the direct sound. And in another test scenario, I left the reverberation constant over all directions and over all positions. Again, in one case, only like in one case, direct after the direct sound, and in another case, 50 milliseconds after the direct sound. And the participants had to, on the one hand, rate audiovisual plausibility, and on the other hand, the similarity to the measured reference. And it was very interesting that in the direct case, so when the loudspeaker was turned towards the listening positions, even severe modifications of the early reflections did not affect the plausibility. So that means when we want to use binaural room impulse response interpolation to create room impulse responses for a whole listening area, we can still be pretty open or inaccurate about the early reflection pattern. And it should still be fine as long as the direct sound is strong enough in energy. So when we're moving directly in front of a loudspeaker, for example, then it will be fine for plausibility. But in case the listener is behind the loudspeaker, so in the indirect reproduction case, as I called it, then the modification of the early reflection pattern in the way that we swap the left and right channel, so that the early reflection pattern doesn't match the room anymore as we see it, that really destroys the plausibility, because it really affects the localization and then the audiovisual alignment with the loudspeaker that is supposed to be the sound source doesn't work anymore. and then the plausibility is completely destroyed. And that's interesting to see. And another interesting case is that if we use these modifications only after 50 milliseconds after the direct sound, which was in that case the estimated mixing time of that room, then these modifications again did not have a severe audible effect. So then again, the plausibility was fine. So what we need to keep in mind, or what we can learn from that experiment, is that on the one hand, when we want to test binaural room impulse response interpolation or extrapolation, then we need to use a critical test scenario to test whether this method really works. I have given a list of different methods that have been proposed for interpolation, extrapolation, or oralization for microphone arrays. But I think I did not find many studies that really had a critical test scenario to show that this method is working. So yes, but what we've also learned is that if we apply all these modifications after the mixing time of that room, it seems to be fine for the plausibility. And what we've also learned is that the image shift effect, so the early reflections that influence the perception of or the localization of the sound source, that this is very important for the audiovisual plausibility. So in case we have early reflections that influence the localization, then it's very important to reproduce them accurately so that we don't get this problem with the audiovisual plausibility. Okay, then we have another case where visual impression raises certain expectations in the listener. And that is, for example, if we see such a kind of wall corner or edge of a wall. So we have here a sound source, and we have a diffracting edge here. And in this study, we looked at two different rooms, a bedroom with a reverberation time of 0.34 seconds and a kitchen with a reverberation time of 0.5 seconds. And we created these three different sound zones, or zones, diffraction zones. One is the shadowed, which is basically the case where the lowest energy, the lowest diffraction energy will arrive. And then we have the near zone, near to the edge, diffracting edge. And then we have the far zone. And we investigated the plausibility of the different room, the kitchen. And we investigated the plausibility of the diffraction, or how the diffraction influences the plausibility, and we could show that it is important, it matters, it significantly increases the plausibility in this case. And we used the Boyd-Tolstoy-Medwin model to model that. And what was interesting in addition was that in this shadow zone, in addition to the diffraction of the direct sound, also the diffraction of the reflections was relevant for the plausibility, or caused a significant improvement of the plausibility. Yes. And again, about the reverberation time, what do we expect there? We tested that also in an augmented reality scenario. So that means that the listener is really inside the real room and hears the real room. And if we want to create then the virtual sound source into that room, we conducted a study on that expectation too. And for that, we used again the measurements along this 2-meter line in the seminar room, and modified the late reverberation in a way that we could scale the reverberation time of that room. And we used scaling factors of 0.6, 0.8, 1 second, and up to 1.8 seconds. So the original reverberation time in that room was 1 second. And if we use these different scaling factors, we get reverberation times from 0.6 to 1.8 8 seconds. And the participants had to rate the externalization and the audiovisual plausibility for each of the different scaling factors. And here are the results for that. So what we can see is that the externalization was not significantly affected for the different reverberation scalings. So even if we reduce the reverberation time or if we increase the reverberation time, the externalization was not significantly affected, only by the anchors, but that was the goal, right? But when we look at audiovisual plausibility, so that means that the listeners could see a loudspeaker, and that was supposed to, the auditory illusion was supposed to be that they have the impression that this loudspeaker is playing, but it was only playing over headphones. And we asked the participants, do you have the impression that this loudspeaker is reproducing sound? And that was rated on a scale from 1 to 6. And we can see that it was still the best, always with the original reverberation time. But it was still also plausible or equally plausible in a range around that original reverberation time. So for example, 4.8 seconds, slightly reduced. And in the position dynamic case, we can see that this tolerance range was even larger. But we can also see that for smaller reverberation times or larger reverberation times, the audiovisual plausibility was affected. And that was because if the reverberation time was smaller, then the sound source appeared slightly in front of the loudspeaker. And if the reverberation time was longer, it appears slightly behind the loudspeaker and even slightly blurred. So the audiovisual plausibility was not, not at the same level anymore. So yeah, audiovisual plausibility is affected by smaller deviations of the reverberation time and externalization. So therefore, it's the more critical attribute that we can use for evaluating the matching of reverberation. Okay, and then all these studies that I've presented now were about creating auditory illusions in known rooms, but what happens if we have unknown rooms? And especially when we want to create extended reality. So we do not want to only add virtual content to the real environment, but we also want to modify the appearance of the real environment. Then we have to work with these hearables that kind of cover the ears and have some microphones, and then can analyze the real environment and modify that, or selectively let through some of the sounds. So we have on the one hand the acoustic environment that needs to be analyzed in real time and maybe separated. So we need some source separation or source detection and localization, and maybe even some sound theme classification. So this is where we can really benefit from a lot of artificial intelligence or machine learning approaches that have been studied in the different fields. And in addition, we can create a desired virtual acoustic scene and add these contents to the real environment. That needs to be combined to overall create this virtual mixed reality or extended reality scenario. That's a bit of the outlook. That's interesting, for example, for different scenarios like listening to music in loud environments. So there, often we use headphones that allow for acoustic noise cancellation or acoustic noise control. But sometimes we still want to hear some specific sounds in addition. So for example, if we are at the train station, we want to hear if some information is announced about our train. And then it would be nice to have this information come through the music as well. So we need some algorithm that detects that currently such an announcement is going on and reduce the music, for example, so that we have this kind of selected hearing case. And another scenario where this is relevant is understanding speech and noise. For example, if we have a super complex room, it's very difficult to focus on specific sounds, and it would be very helpful to reduce the sounds of certain room areas, maybe, so that we are more able to focus on a specific sound source. So because, for example, the cocktail party effect, we know that this is affected by age pretty early. That's one of the first things that is affected by age, capability to use the cocktail party effect. Okay, and another scenario where this is interesting, this kind of mix of virtual and real, is in the augmented or extended reality case, when we have some object that is occluding or shadowing certain elements of the real environment. For example, we want to create a virtual person that walks around in the room, and we have a real loudspeaker playing, and the virtual person would walk in front of this loudspeaker, and we have kind of the expectation that we hear a shadowing effect. But if it's not there, we will have reduced plausibility, or the plausibility will be affected. So this is where these kind of systems will be interesting. And in general, in situational awareness, so for example, augmented or extended reality sounds are explored also for firemen or for astronauts, for people that fly to the universe, to different planets, where we cannot hear anything. And there it's interesting to create, on the one hand, an audio presentation of the spatial environment, to increase the situational awareness, because for them it's also difficult with their helmets to move around and look around. So there it's helpful, and at the same time they have to keep an overview over hundreds of measurement values, so that they don't get in trouble, and it would be helpful for them to always focus on selected sounds at a specific time, and with that we could help with such a system, for example. But these are also just some selected situations where selective hearing could be helpful. Yes, and how do we get that? So on the one hand, we have the active noise control of the real environment, and we have, on the other hand, hear through methodologies or equalization effects that correct the impact on the acoustics of the real environment. And both needs to be combined in order to achieve selective hearing. Again, this is just a very small selection of example studies that have been conducted in this field. A lot more are available already, and we just need to put it together in the end. I think that's the current task, and a lot is happening at the moment there. So this is a really hot topic at the moment in this field, and that's kind of the end of my talk. So what I want you to take home is that augmented reality or extended reality can improve the lives of people, so let's make it work. In known rooms, we know that we can achieve authenticity or the acceptance as real. We know that audiovisual plausibility is a more critical construct or attribute, an externalization for the perceptual matching of room acoustics, and for the evaluation of your system to turn around the loudspeaker. So of course, just an example, but find a good critical test scenario. And for unknown rooms, only smart combinations of efficient algorithms and perceptual optimizations can succeed. For achieving good selective hearing system, we will need machine learning or artificial intelligence, and for that we still need a lot of data sets. I think that's it. It's my former group. where I would like to thank, and that's my current group, who I would also like to thank. And now I want to thank you.
Thank you, Annika. That was really good. Thank you very much. Does anybody have any questions for Annika? You can put them in the Q&A box. I can't see any questions.
It was a lot of content and quite complex, different aspects of it.
It's all good. Okay, so if there is no question, we've got one now. Can you see that, Annika?
No.
Okay, it's from Thomas. He'd be keen to hear about the boundaries on plausibility in VR for creative applications, knowing how to play with this and having things pop in and out of plausibility.
Absolutely, that's a very interesting question. So that was the last point of my what to take home. So I think that still needs a lot of exploration. I mean, the experiments that I have conducted, they have all been looking into the realism or the perceived realism of the sound sources. So I think with a lot of creative sound design, I mean, it is artistically a desire to also modify the room. For example, change the size of the room. How far we can do that depends a lot on how we present it to the user in terms of the sound design. So I think there we can come up with abstract sounds or abstract oralizations. And I think that needs artistic exploration, but also scientific exploration. But I don't have an answer for you now, but this is still an interesting field to be explored.
Thank you, Annika. Are there any further questions before we finish? I think that's it for today. Thank you very much, Annika, and thank you everyone for joining. Thank you very much. Bye-bye.